帰ってきてるわ。Professor Saint Abbas, could you share your screen?
Good evening, Professor Hanada. How are you?
Yeah, good, thank you.
I will just share my screen, but
Yeah,
when I
yeah,
show my screen, I won't be
because
able to see. I won't be able to see anything. Um,
uh
so let me
your
try.
talk will be start in 5 minutes.
Sure.
Good. We will start your invite talk in 3 minutes.
That's okay. Whenever you're ready, thank you.
Good evening, everyone. Uh, Welcome back to the virtual invite talk. My name is Hisashi Handa. I'm honored to be a chair of this invited talk. Now, it is my pleasure to introduce our invited speaker, Professor Hussein Abbas. Professor Hussein Abbas is a full professor at University of New South Wales in Canberra. He is the founding editor-in-chief of the IEEE Transaction on Artificial Intelligence and an IEEE Computational Intelligence Distinguished Lecturer. His research interests are artificial intelligence, cognitive science, operations research, and robotics. The title of this talk is that Explaining Explainable Artificial Intelligence. Professor Hussein Abbas, please start your talk.
Thank you very much, Professor Hanada, and thanks for the conference organizers for inviting me to give this talk. So I know it's for many of the people attending the conference, it's quite late at night. So I decided to make the talk as simple as possible, and hopefully you will get to see that it is really simple. So let me just first make a disclaimer that anything that I would be saying is just I'm responsible for anything that I will be saying, and it doesn't represent the official views of any collaborator or any funding agency. So I will start with a quote, and that's a quote that get used a lot in explainability. It's by Aristotle. And he said, men don't think they know a thing unless they have grasped the why of it. And it's really an interesting talk because it connects knowledge to reasons. And what my understanding of it is that we don't really have, we can't make any claim that we have complete knowledge if we don't understand the actual reason behind the events behind the knowledge that we have. So with this in mind, I hope that this communicate to you that explanation is really a significant topic, and it's a very much close to my own heart. So our topic today is explanation. So the first question that would naturally ask is why? Why should we care about explanation? And I'm not going to get into the reasons of why we care about explanation. As a matter of fact, if you are attending WCCI in person, there will be a panel in 2 days on Wednesday afternoon. And in this panel, we will be discussing explanation, and we will be having 2 hours just discussing explainable AI. So I will leave the why do we care about explanation to the panel. For now, you can see a long list why explanation matters. Traceability. If I would like to trace causes, if I would like to trace why certain things happened, I need explanation. And any type of auditing in organizations, I need explanation for it. The legal system, pretty much, it is all based on explanations. Its reasoning is a very fundamental and an integral part of the legal system. So for legislative reasons, I also need explanation. And accountability, transparency, trust, and the list goes on. So come to the panel if you would like to see us unfolding each of these concepts. But for now, you can see that there's a long list of reasons why explanation really is important. So you would ask then, what is the problem? So explanation sounds like a very natural and common word. We almost all understand when we say, explain this to me, you will all have an answer. and you will explain the phenomena to the person who's asking. So if we can all understand what explanation is, so what is the problem? Actually, the thing is that we may all understand the explanation is in the context of human being, but it doesn't necessarily mean that we all understand what explanation is in the context of AI. And it also does not mean that we all agree on the definition of explanation. So what explanation is can be a central point for debate by many people. And because of that, when you look at the literature, you will find a very large number of diverse views and definitions about explanation in the literature. Not only that, our previous speaker was talking about interpretability and explanation. If you go to the literature, you will even find people who will mix interpretation and explanation. So, and sometimes people will even say, don't bother. If I'm talking about interpretability, I'm talking about explainability. If I'm talking about explainability, I'm talking about interpretability. And unfortunately, none of this really helps because when we are mixing our understanding of these concepts, it confuses people much more. But what is the implication of that? The implication is that if I would like to achieve any of the Y's, accountability, transparency, legislation, if I would like to achieve explanation in any of these things, I have no objective way of defining it. And if I don't have an objective way of defining what an explanation is, I can't give it to a system engineer or to a software engineer to tell them, here's the requirement, here's your software requirement. So I can't really ask for people to implement explanation if I can't tell them very unambiguously what explanation really means. And that is the real problem that I'm trying to solve, and that is the real context of my talk to you today. I would like to come up with concrete definition of what explanation is and distinguish this definition from interpretability, explainability, transparency, predictability, all of these concepts. So how will I do that? I will go through three steps. The first one, I will use explanation to explain explanation. So in the first component, I will be talking in very much plain English, and we will just explain explanation in English, looking at what it means, and we with example showing what explanation means. Then after that, I will have a few slides where I will give you formal notations. I know it's late at night, so I will not get into the details of the mathematics, but I will just give you a very formal definition of what an explanation is. And that's really my objective, is to come up with this formal definition. Then at the end, I will share with you some of the work that we've been doing in my group in this area. So let us start. So let me start by introducing to you a number of agents. And these agents actually come from the classic communication network literature. So I will introduce you to Alice. So when we talk about Alex in classic communication, we are talking about the agent, whether it is the AI or the human who is sending the message. So Alice is the sender of the message, and it's a very famous name in communication. The second one is Bob, who is receiving the message. So you will see at the top of Alice, there's S, and at the top of Bob, there's an R. So S and R, pretty much sender and receiver. Why do I choose Alice? Because that is in the classic communication literature. I didn't come up with these names. So normally we talk about Alice and Bob. So you have Alice, who is the sender, you have Bob, who is the receiver. And in between them, we would normally be talking about the communication channel. So when Alice would like to send a message to Bob, it will send it through this communication channel. In the old days, this communication channel was just modeled with physics. It was just the wire that transmits the message. But today we have intelligent communication channel, which calls for a third agent, which I will call Daniel. So Daniel takes a message from Alice and delivers a message to Bob. So we have sender, we have receiver, and we have the carrier of the message. But there's another agent in this equation which we shouldn't forget about, and that is Carol. Carol is sitting outside the system watching it. It's an observer agent. So I have a sender, I have a receiver, I have the communication channel, and I have the observer agent, which is Carol. Now, I introduced to you the ABCD family. Um, Now, what each of them will be doing? I will be using them for different objectives to explain to you explanation. So before I do that, if we go back to the literature and we look at one of the famous philosopher, David Lewis, David Lewis came up with two senses of explanation. In the first sense, he said, an explanation is an act of explaining. It is the doing of explaining. Now, that's really an interesting definition because when we say an explanation is an act of explaining, what it means is that explanation is not about the ground truth in your system. Explanation is when Alice is explaining to Bob, what Alice needs to take into account, it needs to take into account what Bob knows. And Alice can explain to Bob by reordering information such that they make sense to Bob. But reordering the information may not be consistent with the ground truth in the system. So an example of that, if you would like to explain what a neural network is to someone who has never studied neural network, you might come and say, if you go and you would like to bet on a horse, um, the neural network can come and tell you which horse will win. Now we know mathematically that's inaccurate. We know that this is not an explanation of a neural network. Someone else might come and say neural network is like how the brain works, and we know that many of the architecture for neural networks that we have mathematically don't carry any similarity to the way the brain works. But it's an explanation that is using the receiver knowledge, reordering the information such that the receiver understand the phenomena. Lewis talked about a different type of explanation, and he said, does anyone know it? So now Bob get a message, and Bob is asking, does anyone know it? What really this entail in philosophy is that Bob is assuming that explanation exists. The fact that there's a model, there's a physical system, there is a message, explanation is part of any system. It's like in the scientific method, explanation is part of the scientific method. So Alexander Baird came and mapped these two senses of explanation into two types. The first one he called S explanation, and S stands for subjective explanation. So subjective explanation is when an agent come and try to explain, the explanation does not constitute part of the way things are. The explanation is a way of convincing someone with a phenomena or with a system or with an objective. That is one type which maps to the first sense that David Lewis talked about. The second type of explanation is what Alexander Bird called the O explanation, which is O stands for objective explanation. And here, explanation exists and is waiting to be discovered. So explanation is not what Alice will tell to Bob. Alice does not hold the explanation. but the system that Alice is operating on is holding, is the owner, is the custodian of the explanation. So now we are talking about two types of explanation, the S explanation and the O explanation. So let me speed up a little bit because I'm taking far longer than what I should. So let us now look at Alice. Alice would like to send a message to Bob. So Alice would have something like a system, and that's what I will call the data generation oracle. This could be an organization, it could be a mathematical model, it could be anything. So this data generation oracle is going to generate data. And the data will look something like that, which is what you will get in a classic database, just a bunch of number X and Y. And now Alice would like to send to Bob this data. Remember something, that the objective explanation, the actual explanation of this data is residing within the data generation oracle. It's not residing within Alice. Alice is just sending the data as a message to Bob, but the actual explanation is residing within the data generation oracle. So now Alice would like to send this data to Bob. That's that's great. So we come now to Daniel. Daniel is going to carry the message, but now Daniel decided, I am not going to send the message as a table. I will send the message as a scatter diagram or as a bar chart. Daniel made the decision in the communication channel that no, I'm not going to send this data just as data. I'm sending it as a scatter diagram. Now, when you look at this scatter diagram, this scatter diagram has the data embedded in it. It did not really add any objective information to the data that we have. The bar chart did not add any objective information to the data that we have. Yes, you come and say, but when Bob get the bar chart, or when Bob get the scatter diagram, Bob will think about this data in a different way. Absolutely, this is perception. But even if I send Bob the data as numbers, Bob will think about this data in a different way. We are not talking here that the representation has not changed the perception of the data. What we are saying is the representation has not changed the objectivity of the data. So that is very, very different. And in this case, we will call it faithful interpretation. So Daniel interpreted the data, but Daniel did not add any false information in the data. Daniel did not add any information that does not exist in the original data on an objective level. But now let us think that Daniel is cheeky. And what Daniel decided to do, Daniel said, okay, I mean, I'm not going to send this data. Maybe I will need to actually do a piecewise linear approximation of the data. Or guess what? You know, this data, I can actually fit it into a sine wave. And when I'm sending the message, I am sending a single sine wave, which means it's a very good compression for this data. So it's a perfect compression. I just send the parameter of the sine wave and the ID of the function, and Bob will get this message, and I'm minimizing transmission in my communication channel. Now we have a problem, because when we look at the sine wave and when we look at the piecewise linear approximation, none of that, there's nothing in the data that carries any information to suggest that any of this is valid. So that is what we will call unfaithful interpretation. The interpretation added false information in the data. And this touches into something which is very close to my heart, because we worked on machine learning for translation a few years back. And there's something in translation called the translator invisibility. And when you are translating from one language to another, the translator needs to be a good translator, need to be very, very careful not to add information or not to exclude information from the message that they are translating. So interpretation is exactly like that. When I am interpreting, I should be faithful in the way I am interpreting. I should not be adding any information or excluding information. So now I can actually give you the formal definition of interpretation that we are using, where here interpretation is a mapping from a sentence in one language to a sentence in another language. And possibly I could map from between sentences in the same language. This interpretation is faithful when it does not introduce unverified information. This interpretation is unfaithful when it introduces unverified information. So now we understand what interpretation is. Let us move to Bob. Bob got the data as bar charts and maybe as numbers. And Bob came and said, hmm, but remember when Alice generated this data came from the data generation oracle, from the organization, from the model, from whatever. So Bob said, okay, let me try to actually fill this gap. And Bob may have made some valid assumptions that what is lying in between should be linear, or maybe this is a perfect sine wave that generated this data. And Bob pretty much used this smooth nonlinear function to approximate the data. That's what we call inference. So inference here is not an ad hoc way like what Daniel did. Daniel just did an ad hoc way. Daniel just wanted to compress the message and thought I will compress it by having a sine wave. And by having this sine wave, Daniel lost the information. Bob is doing something like we do in machine learning. We do informed decisions, informed approximation. So we come and we fill the gap between these data points using models. That is inference. And now explanation is about this inferencing. So let us now see a definition for explanation. Explanation is a sequence of expression in one language that links cause and effect. When Bob filled the information in between, almost Bob built a sequence of transitions from this point to that point. And as Bob was building this sequence of transition, obviously it's based on some assumptions that Bob believed that these assumptions are legitimate assumptions. But Bob built a, a sequence of transition from this point to that point. So now we come and say, okay, so if I would like to ask why to Alice or to Bob, I come and say, why this value is like that? Why when I have X this value, I have Y that value? For Bob to really answer why, Bob needs to have access to the way this data is generated. Bob needs to go back and access the causes. And how does nature work? The original system that generated this data, Bob needs to be able to explain the causes for why this value is as it is. But the second type of explanation I can seek from Bob is how? How did you approximate that? What are the principles that you've used to approximate between these 2 points? Fantastic. So now we have these two type of questions that Bob would like to ask, and this type of question is either whether it is why about some sort of causation, or how, which is more about the principles and the methodology for inferencing. So if we would like to summarize that, interpretation is about knowing that, explanation is about knowing why and how. interpretation is about the descriptive knowledge, explanation is about the explanatory knowledge. So, but life is not simple because when Bob tries to explain, remember, Bob could come here and explain this transition by coming and saying something mathematically that another human being may not be able to understand. So what Bob might need to do, Bob might actually need first to explain this mathematically, then after that needs to translate it into a language that someone else understands. So now Bob is generating explanation first, then is using interpretation so that the message is understood by the receiver or the listener. So when we look when how we are generating this type of explanation, we will always be faced with some sort of trade-off. The language expressiveness, how expressive the language is. So for example, if I'm explaining to a human, I would talk about a language expressiveness. If this human is an English speaker, then that's a very high level of expressiveness. That's if I am talking in mathematics, that is low level of expressiveness for someone who doesn't know mathematics. Compactness is the message length, so or the model length. So that is a neural network. I can, for example, if I would like to map a neural network in a decision tree, I could be generating a univariate decision tree. A univariate decision tree of an infinite size can be representing this neural network. So the decision tree is not compact, as a neural network might be compact. And performance, I might, for example, have a set of rules which are expressive and perhaps medium level compactness, but in terms of performance, because you are using some sort of linear approximation, there are gaps between the lines that sharp turns between the lines that create error. Well, as if I'm talking about a smooth nonlinear function, these will have less error around these needs, around these transitions. So I am trading off when I am choosing my model. One model might be low in expressiveness, low in performance, but high in compactness. So this length of the line mean that you could interpret it as either it's low or high. And another model will have the opposite to that. And we need to decide on this trade-off. What this actually means is that sometimes when I would like to explain, I need to make some sacrifices. So we will come to see in a couple of slides how we handle these sacrifices. So before I conclude the first part of my talk, it's really important to link these concepts. And what links explanation and interpretability is transparency. So that's a paper where we have an architecture for transparency, and I will explain more this concept in the next slide. So interpretability is about the language that I'm using. I am translating from one language to another. Explainability is about the logic, is about cause and effect, is about the causality, is about the inferencing chain. It's about this logical chain that I have arrived at a conclusion or I can use to justify a conclusion. And predictability is about uncertainty. So I haven't explained predictability. So we would normally say in this part of the literature that the more predictability, the less explainability is needed. What does this mean? Let us assume that you are telling me something and I'm asking you why. Why did I ask you why? I asked you why because I'm missing information. But now let us assume that before you tell me something, I can predict what you will say. Maybe I would still ask why, but I will ask less whys in this case. I will not always ask why, because the fact is that I am able to anticipate what you are saying. It means that we are synchronizing. It means that we almost like understand each other. It's almost like when you are talking to someone and before you complete the sentence, they complete it for you. They don't go back and ask you, why did you say this sentence? They will be less likely to do that. So predictability is the ability of the listener to anticipate the consequences and the meaning of the message being communicated. And by doing it this way, we discover that we have a cycle that connects the logic, interpretability, and explainability. And that is discussed in detail in this paper in the Royal Society, in the Philosophical Transaction of Royal Society. And I'm happy to share my slides with anyone who's interested. Transparency, the model that we have, it says that transparency requires these three building blocks as fundamental building blocks. So if you would like to build the transparency, you need to have explainability, interpretability, and predictability. But if I go back to this slide, which I don't have time to explain, um, this doesn't mean that you need to have all three at the same time. You may go with one without the other, and you still achieve transparency. So when we talk about AI, we always talk about representation like a neural network. And in this particular case, when we talk about interpretability, we are talking about transformation. So I don't change representation, I just change the representation language. So when I'm interpreting, I need to be faithful in my interpretation, and I move from one language to another, from one representation language to another. When we're talking about explainability, we are really talking about integration. So the listener is trying to get the explanation and integrate it with what they already know, so that they believe, they understand what are the causes, for example, or how things work. And we talk about predictability, we are talking about projection. So representation, transformation, integration, projections, these are our four means in mathematics to actually model these concepts. So now I know it's late at night, but I only have three slides with symbols. So I need now to explain to you the formal definitions, because remember my objective, what I said in the beginning, my objective is I'm not just disambiguating these concepts, I am trying to make sure that I can actually give someone in system engineering or requirement engineering concrete definitions of explanation, interpretability, predictability, transparency that they can implement, and they can become accountable when they implement them. And because of that, I need something unambiguous. So I have my agent here, and this agent has its internal knowledge. Now, when this agent is trying, if this agent is Alice, and Alice is trying to send a sentence to Bob, what this agent will need to be able to do, it will retrieve subset of its knowledge, and based on what language Alice speaks, this agent will need to transform this knowledge into a language that Alice can understand, can speak. But also it needs to take into account Bob. But you can see here that when Alice translate this knowledge exactly to a sentence, if Alice does the translation in a faithful way, Alice is doing faithful interpretation. But Alice is also doing objective interpretation. That's what we talked about in terms of what we said in the beginning. But in the beginning, we talked about subjective and objective explanation. Here, we are talking about subjective and objective interpretation. So when Alex translates this knowledge exactly into a sentence without losing information and without introducing unverifiable information to this knowledge, Alice is doing interpretation, objective interpretation. But remember what I said about subjective explanation in the beginning, and it holds the same for subjective interpretation. When Alice sends this message to Bob, Alice needs to take into account into account what Bob knows. So Alice may start introducing unfaithful interpretation here so that Bob, when Bob gets the message, can understand it. And the same when Alice is getting a message from Bob, it needs to translate it back and update this knowledge. Okay, so let us look at these symbols very, very quickly. It's really quite simple. What we have here, we have an agent. This agent has a knowledge base. This knowledge base consists of two things. One is a set of axioms and some set of rules. These rules are not necessarily symbolic rules. These rules might be neural networks, might be classifier systems, might be decision trees, might be new fuzzy system, whatever these rules are, it doesn't really matter how they are represented. So we have our knowledge base here. The agent also has a set of language available to the agent. So the agent can, for example, speak English, can speak Japanese, can speak Chinese, can speak French. The agent has access to some language that it can use to communicate this knowledge. And LI is a language among the languages that the agent know. And in every language, the language is defined as a set of sentences by the agent. And the agent will start now doing pretty much when it retrieve a piece of knowledge, it needs to retrieve this piece of knowledge and transform it into a sentence. So when the agent is sending a message, it will take a knowledge from inside, translate it into a sentence before it sends a message. When the agent receives a message, it will do the opposite. It will do the inverse of this function. It will take the message in a language and it will translate it into a piece of knowledge for the agent. So that is almost like what I will be talking about next in terms of when these agents are sending to each other neural network or symbolic rules. That's exactly how we do it. And obviously, we need to have a knowledge update function. Every time a piece of knowledge arrives to the agent, the knowledge base needs to be updated. So now we can have the formal definition of interpretability, and you can read this paper to read about explanation of these definitions. So interpretability becomes almost like the transformation from one sentence to another sentence, where the first sentence belongs to language I, the second sentence belongs to language J, and both languages need to be known to the agent. So the agent need to be competent in translating between these two languages. And remember here that I did not have any condition that I doesn't equal J. The agent can be translating from a sentence in the same language to another sentence in the same language, for example. Explainability is this sequence of transition that I need to make. It's a sequence, you can think about it in terms of causality, for example, but that's a limited way of thinking about it. It is just transitions. So you can think about it as, from reinforcement learning perspective or neural time series perspective. It's a set of sequence where the agent would like to come from an initial belief. So that is the initial belief of the listener. When the listener say why, that is the belief of the listener, and the agent would like to reach an effect that is consistent with the listener knowledge through this sequence. So explainability becomes this set of transition from the initial belief to the end goal. Predictability is just a projection, as I said. You can read the paper for details, and transparency model is a combination of interpretation, explainability, and predictability. Okay, so before I get to some of the examples that I will show you today, I need to present to you an abstract measure of explanation. So that's an abstract measure. I'm calling it universal, but it's really an abstract measure, which means that if we would like to define it, we can actually instantiate it in lots of different ways. So if you think about the agent existing knowledge, KB, so that's what I already know. You come and tell me a sentence. You send me a neural network, or you tell me a conclusion, or you tell me a message. That is S. The distance between what I know and what you are telling me is what we call the expected gain. Now, if this distance is huge, then I am missing a lot of information, which means that your explanation will make me so happy because your explanation will fill huge gap here. So the expected gain, I will ask for an explanation when this distance is high. If KB, if the sentence I am getting is already within my knowledge, then in this case, there's nothing new. Then my expected gain is zero. The actual gain is when I get the explanation and I integrate it with this sentence and I measure that relative to what I already know. When this distance closes, then the explanation becomes effective. So if what you are telling me is already something that I know, this distance is zero. If what you are telling me doesn't exist in my knowledge base, this distance is infinity. Why am I explaining? Because I need to minimize this distance. So now how do we do explanation? And I think there was a question in the previous talk about neural network, and I will talk to you about how we explain neural networks here. So, but before I do that, I need to tell you a couple of things. One is that I have an agent here which say, I will do and I will explain. So that's like the old export systems. The old export systems, the rules I am using to infer an action are pretty much exactly the same rules that I will use to explain. But nobody said that, you know, that is like, the objective explanation. The explanation reside within the system, and therefore the system action production equals the system reason for why it produced an action. But nobody said that this has to be the case. I can separate between my explanation and how things work. I can have here a neural network, but I can explain it using using another mean. So these are two agents. One is saying, I will do. This agent will say, my responsibility is to explain what this agent does. Now, remember, Carol Carol was the agent who was observing the communication channel. So now here is Carol coming back to us. Instead of I will do, I will explain, I can also have an agent which is say, I will observe, I will explain. So that is Carol. Carol is not part of the sender, the receiver, or the communication channel. Carol is just sitting outside looking at that. And Carol may have incomplete information, but Carol might come and say, I'm going to observe and I'm going to explain. And equally, I can separate the two. I can separate I'm going to observe from I'm going to explain. So this gives us this space of executor, observer, inference, and explainer. Um, and I'm noticing that I'm running out of time, so I will start speeding up. Um, so what this actually means is that we could actually separate action production from explanation. So I can have an agent which is responsible for action production. This agent might be, for example, doing an artificial neural network. So I'm using a neural network, like the examples that I will show you next. I'm using a neural network to produce actions, but I am not explaining that using a neural network. I'm not explaining what the neural network does exactly. I am actually approximating this through an explainer. Um, it will take me time to go through this in details, but it should communicate to you the message that we can separate action production from explanation. Now, this takes me to the last component of my talk. And everything that I will say now exists in our paper. So the fact is that I will be speeding up and I will skip some stuff should not annoy people because you can always go to the papers and have a look to read in details. What I will explain here is a system that one of my PhD students, and it's also captured in these two papers here, implemented, where we have multi-agent systems. These agents pretty much, if you think of for the time being as two agent, so the system had many agents, but for the time being, think about it as two agent. So you have a sender and receiver. Each of these agents has their knowledge base. Now, the way these agents work, they use artificial neural network to take actions. But because there is Carol sitting here, Carol can see the messages going between these agents. And if I'm doing transfer learning, Alice needs to send some knowledge from its own knowledge, something like a neural network, to Bob. But if Alice sends a neural network to Bob, Carol will not understand that. Carol doesn't understand neural network. And also, Bob is getting a huge neural network, and Bob has no idea how to integrate this huge neural network with the neural network that he already has. So we said, okay, so why don't we separate the two? Why don't we actually, Alice is going to operate with a neural network, but when Alice sends the knowledge to Bob, we will take this neural network, we'll transform it into symbolic knowledge, and we will project it into a set of rules. And Alex will decide how to interpret these rules in such a way that Bob can understand and Carol can understand. So Alice will interpret the rules and will send it to Bob. And now Carol is sitting here watching these messages going between Alice and Bob, and Carol can understand what's happening between Alice and Bob. But on top of that, when Bob gets this symbolic knowledge, Bob will use some mathematics to project back the symbolic knowledge into neural network and will integrate this in terms of knowledge update function back as a neural network. And the same, Bob can also send the message to Alice, and Alice will be doing the same. So it is pretty much two-way communication. So that is the idea. So explaining neural network is not new. Transforming neural network into knowledge is an old field in neural network called rule extraction from neural network. There's a very long history about rule extraction from neural networks. I contributed in the early days back in 2001 with decision trees. So transforming a neural network into decision tree. I will mention this very quickly. And we have also some contributions in this area. But transferring knowledge comes with knowledge transfer is a big problem in machine learning. One of the plenary speakers today talked about some of these challenges as well. I suggested that given the time, you can read the paper to see the challenges. Negative transfer, when Alice sent a message to Bob, the fact is that Alice learned something. When what Alice learned, when it goes to Bob, it doesn't mean that Alice's knowledge will help Bob, because Bob can be in a different situation or can be in a different context. So what this means is that when Alice sends something to Bob, even so that this knowledge might be high quality from Alice's perspective, it could actually degrade Bob performance. So that's what we call negative transfer. We have catastrophic forgetting. Imagine that Bob is getting huge neural networks and keep saving it. Over time, Bob will have to delete some of the old neural network. And now we have a problem that all the knowledge is not maintained. And obviously scalability and training cost, if you are talking about deep learning and any of these things. So what we did, we came and we said, okay, we will separate action production from explanation. But in this particular case, we just limited the paper to interpretation. So we did just the interpretation component. So we took a state space using reinforcement learning, and we said, okay, I can actually take this and I divide this state space into sub-state spaces. And we said, okay, our agent are not going to see the whole state space. Our agent is going to see only one subspace in these spaces. So we had an agent in each of these boxes. So we had 9 agents. And each of these agents is learning its local state space using artificial neural network. Then after that, it use the architecture that I showed you before to transfer knowledge to other agents before the other agent start moving to another subspace. So we kept the agents moving on this subspace. This paper was presented in IGCNN last year. So if you go to the conference proceeding of IGCN last year, you will get all the details about what I'm talking about here. And when the agent receive a neural network, we had an architecture based on Society of Mind, Minsky Society of Mind architecture that we've been working on for a while. And this architecture integrate these incoming neural networks based on some conditions. And we start looking at the performance of these agents when we are, so our system is called the MIKF, and we have 2 versions of it. One is gated and the other was not gated, and we compared against another one which is HOT, and also against a baseline where there's no knowledge transfer. The agent is learning, continuing learning from scratch everything. And remember that I divided the city space into 9 situations. So as I expose the agents to more situation, this is the accuracy of these agents. So you can see that in the beginning, all the agents saw a single situation. The 9 agents pretty much were identical to each other. When they start going to the second situation and the knowledge transfer kicked on, that is the time the 4 methods started to differentiate, and we keep going until they visited on 9 situations. To cut the story short, obviously, we published the paper, which means that the results are good. We managed catastrophic forgetting. We manage performance. So before I conclude, I would like to also expose you to some ways of doing interpretation and explanation using decision trees. And the reason I'm talking to you about that because they will be my future work. And this is some of the work that we've done on each of these. So dynamic decision trees. When we are so far in the literature, we are talking about interpreting or explaining neural network. Most of the time, they are feed-forward neural networks. But most of the time, we would like to explain or interpret time series or first-degree dynamical system and so on. So that's a piece of work that I did back in 2001, almost 23 years ago now, um, which was looking at how we can transform element type recurrent neural network into a decision tree. Um, the paper also included classic feed-forward neural network and element type, so it proposed both methods. That's another piece of work which was really quite significant here, where we introduced the idea of neural rules. So you take the space and you divide it into conditions, but the actions are neural network. So the conditions are symbolic knowledge and the actions are neural networks. So have a look at this paper published 2008 with Shin Yao, and it's really a fantastic idea that I think many people could build on top of it. The last idea that I will talk to you about, remember when I talked about translator invisibility, the reason we talked about translator invisibility is that we faced with a problem where the data is coming in pairs. So a piece of text that was translated by 2 different people. So you get the data in pairs, and how we can actually build a decision tree that can actually deal with this data. So we devised a new type of decision tree. We call them pairwise comparative classification. And this type of pairwise comparative classification or decision trees has these characteristics. It's almost like relational decision trees, where you can actually build a decision tree a discrimination function that can handle this data that is coming in pairs, so you can distinguish who translated this piece of text. And ontology-guided learning is another idea that we worked on it in the past, and we resurrected it in the last few years, again, to have some sort of interpretable clustering method. So I will skip this. So to conclude, S explanation and O explanation, many people in the literature are really focusing on the O explanation, much less on the S. People on the AI, there's a growing literature on S explanation, especially people who are doing classic planning in artificial intelligence. But our community is somehow focusing in computational intelligence more on the O explanation, and I think we need to combine both. Um, Separation between action production and reasoning is an area which is in almost early stages. There's significant work that can be done, and people who would like to talk about unconventional explanation, if you would like a challenge, go and explain dynamical systems, go and explain data in comparative setting, like the pairwise classification that I talked about, or relational setting. There is a panel on Wednesday where we will be starting with a debate between Professor Alexander Jekov and myself, and we have fantastic people on the panel. Professor John Garbaldi is going to be chairing the panel. Keely Crockett, Ozai Kaimak, and Zhao Souza, they are all on the panel. I'm really looking forward to it, and we will have 2 hours debating and discussing explanation. And obviously, transaction on AI, please feel free to submit to the transaction. This is my last term as editor-in-chief, but I still have 6 months to go. But the transaction is growing significantly, and I'm sure you all know that. So with that in mind, thank you. And I would like to thank all my collaborators. I would like to thank all the artificial intelligence systems that I built in my life. I have learned a lot from them. And I also would like to thank my funding agencies. And I thank Professor Handa and people who are still awake, despite that it's quite late at night. Thank you very much.
Thank you very much for your impressive talks. Is there any question or comment? We have 3 minutes remaining. No, I have a curious questions.
Please.
I very impressive about the formal definition of explanation or interpretations. So slide of within Alice, Bob, Carol, or agent is inside. In the previous talk, your question is sentiment is depends on country or races. In the this in the formal definitions, you employed language. If Alex is Australian and Bob is Japanese, what is happen? What affect for explanations?
Yes, absolutely. It's an excellent question. There are 2 aspects about this question. The first thing is that when I talk about language, I am talking about language in the general sense. So mathematics is a language.
Yeah.
I'm talking about formal languages as well as natural languages like English, Japanese, and French, and so on. Now I come to your question. Um, Human language are really magnificent. And sometimes you will find that they are not equivalent. What this means is that I may have something in Japanese that I can't translate it exactly in English.
I see.
And the same way, I can have something in English that I can't translate it exactly to Japanese. So this is quite different from what I called unfaithful interpretation. In
Oh,
unfaithful interpretation, the agent intentionally, the agent, it changed the meaning, it changed the information in the message. But when I have two languages which are not equivalent to each other, and I am going to miss information, I can't avoid when I'm translating. And a good example for that in our field, when I'm translating from neural network to univariate decision tree,
yeah.
I have to approximate that. They are not equivalent. The two languages are not equivalent. And because of that, that introduces some error, but I am trading off accuracy against expressiveness. So I am sacrificing with the accuracy, but I am going for something that people can understand. Have I answered your question, Professor Hanan?
Yeah, thank you very much. Because my next question is relevance of neural network and humans. It should have different language too. Yeah, very
Absolutely.
yeah, good uh, answers. One guy is uh, question by Professor Takashi Shinozaki. It seems to me that all explanation would require detailed estimation of the model of S. Is such a thing possible?
That's excellent, an excellent
Mhm.
question. Um, I would say that um, in the general case, this is a very, very hard problem because if I understood the professor question properly, what the professor is saying is that if I would like to, if I have an objective explanation and I would like to communicate it to Professor Handa, and I would like to make sure that Professor Handa understand my explanation, then I need to actually have a model of Professor Handa. And if because this model will help me. And as a matter of fact, we all have that, you know, we have all our internal models of each other. We may not be conscious of it. So as a human, we actually do have these models internally, but these models are not highly detailed, and I know they are not highly accurate. So I think my answer will be it really depends on the complexity of the explanation, the complexity of the context, and pretty much the situation that we are in. But that's a fantastic question. I completely agree with you. It's one of the questions which keeps me awake at night. How you can actually do this such that you can actually assure understanding. So assuring understanding requires these detailed estimation models that you mentioned.
Yeah, thank you very much. Time is coming. I would like to close this session. Thank you again for Professor Hussein Abbas.
Thank you very much for the invitation. Have a good night, everyone. Take care.
Have a good night. Thank you very much.
Bye.
Yeah, I would like to close these sessions.いいよね。